the idea arose, okay, why can't we use this, for example, to learn a representative audit sample as well? And this was the idea of applying so-called vector quantized variation to autoencoders. And here the idea is basically, instead of just learning a latent representation in a three-dimensional space, for example, we also want to inject a certain set of code vectors, and these are our audit samples. And these code vectors should also be used for the reconstruction of our journal entries, meaning we want to achieve, based on these code vectors, which can snap to one of the journal entries that we have in the data set. And based on these code vectors, we want to reconstruct the majorities of the journal entries correctly. So we have a dual learning objective here. First, the reconstruction of the journal entries, but at the same time, we also want to learn, based on a limited number of code vectors, to reconstruct most of the journal entries correctly. And therefore, these code vectors become representations for the underlying representations that we are learning here in the latent space. And here we see one example. For example, we see here this two-dimensional latent space that was learned, and we see here the colors. These are the journal entries, and then we see these red dots. So these are the ones that present a representative audit sample for a particular manifold, for a particular population of journal entries that we see here in the data set. So here the idea is really to learn in parallel also some kind of representative audit sampling. In addition, saying, okay, if I want to minimize my sampling risk, for example, as an auditor, what are the different journal entries that I should investigate in order to have a representative sample? So here we see one result with a sample size of 8 samples. And here, for example, depending on the risk appetite, again, of the auditor, we can increase the sample size. And then we see here a much more fine granular representation manifold that we are learning, but as well also sample size. This is quite interesting. Yeah. So
Marco, I just want to add on top of what you were talking about. So it seems that this representative sampling is still like you want to take, let's say, 10% of each group, right? And then I think that in like for auditors, they may also want to look at all the transactions with very high reconstruction errors, as you show in the previous slides, right? So I guess if auditors want to use this tool, they want to look at all those, like the red dots and yellow dots that you highlight in the error reconstruction diagram, and randomly select a percent of each group of representative sample, right? I guess it's like a combination. So you look at the high GDP and the representative of the population.
Yes, absolutely, exactly. That's true. I mean, the interesting thing is here, I mean, usually, and this is also judging from my own experience, I mean, let's assume maybe you're involved in a new audit engagement, for example, and now you're mandated, for example, to audit some kind of data population. Usually what we have is what we had at PwC is either we use some kind of proprietary sampling audit sample generator that was developed, for example, in-house, or we choose to do some random sampling. And what we wanted to achieve with this approach is actually, can we somehow obtain a representative sample of the data population by knowing a lot about the data population? So because usually if in a new audit engagement as an auditor, you don't have a lot of insights of high-dimensional data populations, but you still need to audit it and you need to draw a representative sample. So what you're doing usually is maybe you generate some buckets, for example, based on certain data attributes, and then in each bucket you select a particular sample, maybe the one with the highest amount, with the highest posting amount, for example. But these are a lot of assumptions, right, that you are putting on top of the data in order to hopefully derive a representative sample. The interesting thing is here is that, first of all, when we get the entire data set or a perspective on the entire data set in a two-dimensional space, and at the same time, we can somehow correlate or see exactly where our samples are sitting here. And this gives hopefully a lot more comfort in terms also how a certain sample size was selected. Interestingly, and this is probably an interesting study, is also to compare maybe the sample size that the autoencoder or the vector quantized variation autoencoder proposed with the sample size or with the samples that have been drawn by auditors, and see if there are some white spots maybe Maybe there are some manifolds that based on this manual sampling, the auditors didn't draw, and therefore maybe there's a higher risk in that area. That's maybe one approach. But yeah, exactly. Usually what you want to do, maybe if you think about SAS-99, where you maybe want to investigate fraudulent journal entries, you're definitely interested in the anomalies. But if you think about more the audit sampling standard, something like ISO 315, correct me if I'm wrong, then you want to draw maybe a representative sample. So here's just one example how the autoencoder learns, and I will skip that probably in the interest of time. So maybe just to see one example, and this was actually, this time we used a data set which was also publicly available. So this is the Philadelphia City payments data set. So this encompasses a lot of the payments of the city of Philadelphia for a special financial year or for a year. And we see, for example, there was a sample drawn here in this particular manifold. That we see here that was sample 99, and this is the corresponding sample, audit sample that the autoencoder or the vector quantized autoencoder suggests. And then here we also have at the same time all the different journal entries or all the payments that correspond to the sample here in this high density region. So we see there's a very good similarity between the one that was proposed to be investigated and then all the others. Same holds for sparse density regions, but of course there are also some errors here, for example, because the sample that was proposed corresponds to American Express travel vouchers, but since this is a very sparse region here, it seems like there's also at least one document here, one payment that corresponds to autoparts. So maybe it would be interesting to increase the sample size in the sparse density region. All right, well, does this make sense so far? Or I think there's some question.
Yeah, this makes sense. I just get reminded that one of my colleagues, Nuruddin, he did a dissertation on developing what he called a skipper and a stretcher method to select representative samples. But his approach is more like a rule-based approach. So maybe I will get you connected with him, and then maybe you guys can look at like how are the methods different, and maybe do some comparison.
Oh, that would be wonderful. Yeah, thanks a lot.
Yeah, and furthermore, the outlier detection group have been meeting for a year and a half and comparing a whole set of outlier detection. One of them is neural networks, but I don't think they are doing the deep learning part of it. You should talk to them, maybe even attend a couple of their meetings. I sent a note to Lulu asking her to send the recording of your presentation to them.
Okay, thank you very much. So these were, I mean, maybe to sum up, so what we saw now here in this area is, I mean, we have two tasks, right, that we try to accomplish here with the deep autoencoder neural networks. So one was audit sampling, the other one was anomaly detection. And maybe we have a third task as well, where we say, okay, we have to a certain degree also the chance to explain things in the latent space. So explainability to a certain extent might be a third task.